Welcome back to ECE 442-542. Yes, this is the same class that you were listening to a week ago. It's just the voice is a little different. There's a frog somewhere in that voice. Maybe we'll learn how to filter that out after we get a little bit into this class. We'll learn about filtering, processing signals. Maybe you could do that and you could filter this particular lecture's audio and then it'll sound like a week ago, maybe, if you can do that. Passports are due on Friday. Your first assignment is due a week from that on the following Friday. Here are some suggested office hours. Those are all PM. Question? The question concerned my signature or the signature line description on the passport. I'm not so concerned about you signing that physically if you have no way of scanning that, but scanning documents might be helpful when you're wanting to put those into the Dropbox. If you simply upload it, I know it's coming from you, so you don't necessarily have to sign it. So if it's easier for you to generate it all digitally or in an electronic or soft form, and you're unable to sign it, that's okay. So don't worry so much, but by you submitting it, I'm assuming that's your signature. Is that clear on that? Don't let that be a point of confusion. These office hour times are all PM. Those are not AM times, and I tried to actually establish some consistency. And on Friday, which is the day we don't meet, but I'm thinking that probably our homeworks will be due on Fridays, I'm giving you 2 hours on that day. I don't know why, but I just assume you might be needing more time the day of the assignment when it's due. I would prefer that wasn't the case, that everybody was a few days ahead of schedule, but I'm just kind of going on my experience with establishing. And if these are not going to work out for you, let me know. I hope you've spent some time looking at the website. If you're asking about the passport, at least one student has seen the D2L website, I believe, if they know there's a signature line on the passport. But there's additional material there, readings, resources, notes, videos, and there's also a review or prerequisite section that if you want to try to get yourself back up to speed, you can with different topics that are maybe block diagram, Laplace transforms, state space representation, Bode diagrams. Those are all concepts that would be nice for you to have in your mind as you're moving through the material in this class. Today what I want to do is really just scroll through what we finished up on last time. That's why it says review. I simply want to give you the relationship between a state space representation, the matrices A, B, C, and D, and how you could then write down or find the transfer function. We're assuming single input, single output for most of this class. The capital G of S, the transfer function, will then be in terms of your system matrices. Then we'll get into discrete time. We'll talk about linear difference equations, and we might as well give something that maybe you're familiar with, student loans. We'll do a student loan example. How are you going to pay off these loans? What timeline or what payment schedule will you be obligated to? We'll just give an example, but then tonight you can go home and actually do your own. You can figure out what's going to happen, or maybe how you can save money for your car in advance of making the purchase on that car. Just one application of this class, and so if you drop the class after tonight, at least you can do some time value of money ideas. You're now moving money between time, let's say. Then we will be more general and examine how do we solve these difference equations? I'm assuming you remember how to solve differential equations. Let's now talk about solving difference equations. And we'll do that by looking at homogeneous and non-homogeneous, or equations that don't have a forcing function and equations that do have a forcing function. If we have time, we'll then start building up systems or models by all delay block diagrams relative to maybe what you've seen in earlier courses, all integrator block diagrams. In discrete time, what you really are needing is really just a way of holding things in memory or keeping track of things that have happened in the past. That means you just delay things. You have the output now. Maybe you have the output one time period before. You have the output two time periods before. Can you now linearly combine those to generate the output one time step into the future using maybe the current input, etc. And we'll build block diagrams. The block diagram then, like in the analog case, will allow us to immediately find a state space representation for a discrete time system, or a state space representation associated with a linear difference equation. From last time, we looked at, or we did, this transformation of a state space representation into another model or another way of representing that system as a transfer function. If we're dealing with the continuous time system, that state space representation is really just a coupled set of differential equations. And we modeled that or relabeled that with different matrices. And you might just see me abbreviate that by saying SS2TF. If you start texting this lecture to others, you might want to remember that shorthand, SS pass TF. And then everybody knows what you're talking about. They know you're talking about this model and two different representations of it, one being this structure, x dot. X is a long or a tall, thin vector of state variables. A is our system matrix. It's square. B is the input matrix. If it's a single input system, B is tall and narrow. It's maybe Nevada tall. I'll be using Nevada and Michigan for N and M. One, because I don't enunciate very well, and with frogs somewhere in my system, it makes it even worse. So I'll try to make sure that Nevada is N and Michigan is M. Then we may have Pennsylvania if we have a P. I don't know, Rhode Island if we have an R. I don't know. I may vary these up, but we may need different variables to label some of these dimensions. But M might be the number of inputs. Michigan inputs, typically we'll just have one. B then is going to be one column wide, the capital B matrix. And the output matrix is simply a linear relationship between the state variables and the input and the output. We can Laplace transform both of those equations. One is easy because it's just a linear relationship between y, x, and u. The output equation is easy to Laplace transform. We just have to capitalize the variables and replace the t's with s's effectively. The first one is where we get a little bit more involved with the Laplace transform, and that's simply remembering that the Laplace transform of a derivative is s times the Laplace transform of the vectored quantity. Again, x, little x of t is some tall, thin vector, Nevada tall, N tall. Excuse me. Maybe you didn't hear that in the recording, but I paused. Now if we Laplace transform, we have Sx is equal to Ax of s plus Bu of s. We can combine the like terms that scale x and u. We can solve for capital X of s by inverting Si minus A and replacing in our Laplace transformed output equation what we know capital X of s is equal to. Then we actually end up with the equation that we derived last time, which is capital G of s is C times Si minus A inverse B, and then we add to that mess D. And a lot of times D may be 0. That's our direct feed-through term. That's the coefficient, if it's a single input, single output system, that's the coefficient that directly links the input U to the output Y with some scaling or weighting. Sometimes that's not there in your system. Again, this is SS to TF, and that gives us this transfer function between the input U and the output Y. And I scrolled through that because I'm assuming you already had that from last time. But this just sort of gets you thinking about different ways of modeling systems. And you have to do some of this in your homework. You have to produce maybe a G of S. And I sort of walk you through that process. And it might be an electromechanical system, a DC motor. And you now have to find this capital G of S. What does that look like in terms of the numerator and denominator polynomials making up that transfer function? Let's now get into something a little bit new to this class. We didn't do this last time. Now let's talk about what this class is built on, which is discrete time or difference equations, linear difference equations. These are equations that evolve at discrete points in time, and we usually keep track of that by, let's say, this time index, little n. And as I said before, the example that we will use is this student loan repayment problem. If we're overly optimistic, you don't have any student loans. So the principal is 0, but that would make for a boring example. So let's just speculate that maybe you do have a non-zero value for your loan. And let's not get too aggressive. Let's just say it's $5,000. So maybe it's taken you 5 years to get through, and you've just had $1,000 loan every year. We'll be optimistic, maybe. Maybe not on the 5 years, but on the 1,000 per year, right? You've maybe done this in 2.5 years. So maybe you have $2,500 a year for your loan. All right, there's the principal. And this we will just say is our beginning balance. And maybe this is a little bit high, but let's just say that the interest, it's not a credit card, that could be upwards of 17 or 20 maybe percent. Let's just assume this is 8%. Here is now our annual interest. Sometimes it's helpful to think of this in ways other than just an equation. Can you sort of visualize what's going on in this particular problem, maybe with a figure, with a picture, with a plot. Is there some way to think about what is happening? You now have, excuse me, a loan of $5,000, an 8% interest, and you're hoping to pay this off, this loan. And maybe, I haven't said yet, I don't believe, but let's just assume that we'll pay it off in 10 years, this amount, this $5,000 amount. Is there some picture that we could draw? And maybe to help us draw that picture, maybe we just say, let's call this some variable p sub 0. So we're going to let our initial balance be p sub 0, and can we see a figure or a plot here's our dollars that we still owe. We just said that we're starting with 5,000, so let's say this is 5K and this was p sub 0. If we didn't pay any money at the end of the year, then not only would we have 5,000, but we would have the interest on that amount. Let's just say it's compounded annually. So now we would have not only p sub 0, but in addition to that, we would have this amount that is p sub 0 times r. So this x represents p sub 0. Then we have a little bit more, p sub 0 times r. But we want to knock that down, and the idea is to get that paid off in 10 years. So we know that the payment has to be less than, or larger in value than what we're adding on each year with p sub 0r. Meaning if we now bumped that down some amount, let's say u, then that will drive us to a new value, let's say p sub 1, the value of that, or the balance of our loan at 1 year, at the end of 1 year. And then the idea is that p sub 2 will be a little less than that, p sub 3, until we get out here at p sub 10, and we want the balance to be 0 at that point. We're trying to see how much is this u, this constant amount that we, and you could think of that maybe as something down here, possibly, that you're taking away from each of these accumulated piles of money. That's the balance at 1 year with the interest added on over a 1 year interval. And that's now the picture of what's happening, and hopefully you can sort of see this decay. That's what you want to happen with a loan. You want it to be decaying. You don't want it to be growing. You want your savings account to be growing, unbounded, right? But the loan you want to be shrinking. Now let's create from that picture, or from that idea, let's put that into equations. And we've already said that p sub 0 is our initial balance, r is our interest, p1, we were saying that's the balance after 1 year, and u, the variable u, is our yearly payment. And that's made the end of each year. And what we're trying to do then, we know P sub 0, we know how many periods we need, or we're agreeing to pay this off in, 10, and we know little r, and that's 8%. What we're trying to find is this value u. We can find what P1 is in terms of the variables that we've introduced. We know that we had P sub 0, and this we actually drew in our picture, or tried to. We have P sub 0 plus the interest on P sub 0 over 1 year, and that's simply the balance times the interest rate, so that's P sub 0r. But we want to reduce that by some amount u. And that's now our equation that is describing this relationship between the money in the loan, the payout, or the payment, and the balance of that 1 year into the future. We can combine the P sub 0s so that we could write this as P1 is 1 plus r, P sub 0 minus u. What's that look like at the second year? What's P sub 2? Well, it's exactly the same structure, isn't it? We know what P1 is. We add on the interest over that second year, which is P1r, and subtract u. So this is P1 plus P1r minus u. Same structure as we had to describe the first year, or this now becomes P sub 2 again as this 1 plus r P1 minus u. And from that, it looks like we could generalize this. We could simply replace 1 and 2 with n and n plus 1, or n and n minus 1, depending on how you want to label it. Let's use the P sub n plus 1 is now going to be 1 plus r P sub n minus u. And that's going to be true for n equal to 0, 1, 2, up to 9. Meaning P sub 9 plus 1, or P sub 10, is all the further we want to go. We want that to actually be 0. And this is now not a differential equation, this is a difference equation. But it is really describing some dynamical relationship, and it's associated with a loan, which maybe you didn't think about loans and dynamics before. But now you can. It's just a difference equation. Well, if this is now a difference equation, let's put it into a different form. Let's put it into a block diagram. And now, like I had said in the introduction to this lecture, instead of having integrator blocks, now we have delay blocks and gain blocks and summing junctions, and or paths that interrelate those. In our block diagram, we could say, let me keep that picture, let's say that we have P sub n plus 1 right here. If that goes through a delay block, what's going to come out of the other side? If I have P at time 2, and I delay that, what's going to come out at the other side of that delay block? P one time step in the past, right? P of 1. Here, P of n plus 1 goes into a delay. It comes out as P of n. Now we have two of the variables that we need in our formula. We can create this relationship between those by saying, let me put a summing junction here. The output of that summing junction is the left-hand side of that algebraic relationship. I can build that by saying, let me measure P sub n, scale it by a factor of 1 plus r, and that makes the first piece of the right-hand side of that equation. And I'm now trying to make that summing junction describe that difference equation. The output of that summing junction is the left-hand side, P sub n plus 1, and all the inputs coming into that summing junction are the right-hand side, so this is u with a minus sign. And that's now another way of describing your loan. And now if you go into the bank and you say, here is what I need to negotiate, and give them that block diagram, they'll be good to go, right? They'll go, who is this? Is this some engineer? But you'll go, tell me what we can do. Now, maybe what you do when you go to buy a car is the salesman tries to, let me go check with my manager. When he comes back, you give him this block diagram. And that manager's going to go, where'd you get this guy? Maybe, maybe not. Now, the whole point of this is to try to find u, the variable u. How much are we going to have to pay off every year to knock this $5,000 down to 0 after 10 years? That's the idea. Let's now find u. P2 was 1 plus r P1 minus u. We can write this actually in terms of P sub 0 because we know P1 in terms of P sub 0. P sub 2, and now let's put in P1. P1 was 1 plus r P sub 0 minus u minus u. Where in red is just P sub 1. Or, if we multiply all of that out, we see that P sub 2 is 1 plus r squared times P sub 0 minus 1 plus r u minus u. Questions on where that came from? Now we have the balance of our loan 2 years into the future based only on the starting balance P sub 0 and this payoff yearly amount or yearly payment of u. Again, we're trying, and r is the interest rate. We're trying to find little u, what that value is. Let's now go one more time step into the future. Let's look at P sub 3. P sub 3 is 1 plus r P sub 2 minus u, which if we now replace P sub 2 with that green expression on the right, we end up with 1 plus r cubed P sub 0 minus 1 plus r squared u minus 1 plus r u minus u. And that's P sub 3. And we could just keep doing that. to where, let's say we did it up to capital N. That capital N is now 10 in our example, but it could be whatever we needed it to be. 1 plus r raised to what power? Capital N times the original balance minus, and now that collection of u terms is kind of messy, but we could actually write that, collapse it down as a sum. We have 1 plus r raised to the 0 power times u. We have 1 plus r times u. We have 1 plus r squared times u, and that was with the p sub 3 expression. So we're stopping with the power of 1 plus r, 1 less than p sub 3. So that now we can say something like, let's sum from L equals 0 up to capital N minus 1 of 1 plus r to the L, and that all scales u. That is really what's happening with all of those terms that contain the yearly payment, little u. And really what we want to do is we want to find, we know r, we know p sub capital N, we know p sub 0. It'd be nice if we could figure out s. What is s, or this expression that we've now said is this sum? It's a finite sum. It's not an infinite sum. It's a finite sum. It has a finite number of terms. The sum from little l equals 0 to capital N minus 1 of 1 plus r to the L. Or 1 plus r raised to the Lth power. Did you guys see equations like this in your discrete math class? Math 243. I'm just curious. No? Some yeses, some nos. Now I'm confused. Did you obviously, I hope, didn't take Math 243 in the same semester? Who had this in Math 243? Wait a minute. Before you show me hands, and I don't think you're embarrassed by this. How many did not take discrete mathematics? The grad students probably haven't had discrete mathematics. All right, not very many hands are going up. How many have had 243? Okay, of those hands that are being held up, how many looked at these kinds of equations in your math class? You don't remember? It was a semester ago. Just like the class that I taught you a semester ago, you've forgotten everything. I have a heavy shoe. If I have to take that off and throw it, it could be damaging. No. All right. Well, let's see if we can find what this is, whether you learned this in math, discrete mathematics or not. So leave yourself a little space, because I'm going to actually write above the line that I'm putting down now. So I'm just forewarning you. So let's say that let's write s in an expanded form. We first have 1 plus r to the 0 plus 1 plus r1 plus 1 plus r squared raised to the n minus 1. And this, I hope you're okay with me replacing that with 1. 1 plus r, doesn't matter what that is, raised to the 0th power, that gives us 1. This is now an expression for s. What if above that we look at S times the quantity 1 plus R. Now on the right-hand side, multiply all of those terms by the factor 1 plus R, and that 1 now becomes 1 plus R raised to the first power. So I'm going to write it over here, and I'm running out of space, aren't I? Plus 1 plus R squared. I'll collapse it. I would ideally like it to line up. Here's 1 plus R to the n minus 1, but now we have one more term because we've now multiplied this 1 plus R to the capital N minus 1 times 1 plus R, so that we now have on the top line, I have an infinitely wide piece of paper, so I can just keep going. You don't have that luxury, so I won't punish you. But this is now 1 plus R to the capital N. Are we okay with that? Just multiplying S by 1 plus R on both sides. We haven't really done anything too dramatic. Now what I want to do is I want to take this bottom equation, the left side and the right side, and subtract that from the black line up above. Where on the left-hand side, I actually have S plus RS. And I'm subtracting from S plus RS, S. So what's the result on the left-hand side? I know it's late, but this shouldn't be that. We have R times S. Hopefully you see that on the right-hand side we have a lot of cancellations. We have a lot of similar terms. The 1 is not contained in the top row, so that's going to come down with a negative sign. On the right-hand side, we at least have a minus 1 because we're subtracting the bottom row from the top row. Then everything else in the bottom row gets canceled or cancels everything in the top, and we are left with one extra term in the top, which is that 1 plus R raised to the N, capital N. Again, I wish I could have lined that up better. I should have planned more effectively. But that's now the result of that subtraction of the bottom row from the top row. Is it clear where that comes from or what we end up with? Again, what we're trying to do is we're trying to find capital S. The only unknown in that line below the red is S. We know little r. We know capital N. Minus 1 we better know. We know what minus 1 is. We can now solve that for capital S. Capital S is now 1 plus R to the N minus 1 over little r. We've now found a closed form expression for that finite sum. That finite sum expression, which was a sum of 1 plus R to the L for so many terms, now I've written, or we've rewritten, in terms of little r and capital N. In our particular loan, our interest rate was 8%. That's 0.08. Capital N, we said, was 10. If we use those numbers in the expression for S, we now have 1 plus 0.08, 10 minus 1 over 0.08. We are now raising something that's a little bit bigger than 1 to a higher and higher power, and in particular, we're raising it to the 10th power, so that should be something bigger than 1. It's not going to go too big. If we actually computed it, which I hope I did accurately, it's 2.15892. And I quit. I ran into my mic. Sorry. I have to not cut the corner so sharp next time. Now we have 2.16 minus 1. We have 1.16 divided by 0.08. I'm going to say that that's roughly 14 and a half. Now we can use that in our main equation. That's the equation that we know you were okay with that equation. You didn't stop me before. That's our underlying equation that relates the beginning balance, P sub 0, to the ending balance, P sub capital N, the interest rate R, and this finite sum, capital S, that we've now found. The only unknown is little u, and we can solve for u. We now have in our equation, we have P sub n is equal to 1 plus r to the n P sub 0 minus s times u, where this is 0, this was 10, P0 was 5,000, that was 0.08, and S was 14 and a half. We can now solve that for little u, and little u ends up being $744.83. That's now our annual payment that, based over a 10-year period, will pay off that $5,000 original balance with an interest rate of 8%. What if you were saving in your piggy bank before you started college, and you said, oh, I know I'm going to have a $5,000 loan. Maybe I can save up before, and then I can just pay it off when it becomes due. Let's see what we would have to save and over what length of time relative to this annual payment of $744.83, or $745 a year. So let's just put some numbers together. What if suppose we said, well, I've been doing some odd jobs or had an allowance, and I can save $700 a year. Now, you're not going to be earning, let's say, the 8%. Let's say that we're really aggressive. You've learned what investments So what if we saved $700 per year at 6% interest? Can you sketch a picture of what this looks like relative to the picture we drew before? Do you see a picture now? Do you see these ideas as a picture? And so if somebody writes down an equation and you go, I'm not sure where that equation came from. Well, if you sketch the picture, you can maybe back out or immediately write down the equation based on the picture. I don't know how you're processing this or thinking about it, but maybe the picture would make more sense. What's the picture look like? Or maybe you want to say it's a graph or a figure. Let's say that our first is made at time 0. And let's say this is now our payment, U bar. And we know what that is. That's $700, isn't it? Now, what do we have picture-wise at the end of 1 year? Do we have P0? And that answer actually could be yes, but we also have some more, or it could be no, we have more than P0. So that could have been a yes or no, and I would have had to give you credit if you answered it properly, or if you justified your answer. So that was a vague question, wasn't it? Or an imprecise question. We do have P sub 0, but we have that plus the interest, and the interest is simply P sub 0 times R, and that will give us an additional amount, won't it? Where this P sub 0 here, again, is this U bar. Wait a minute, what do I want to say? We could do it that way, but let's keep these maybe separate. We now have P sub 0 plus the interest that accrues, and we said we're always adding in 700 a year. So now we need to add to that U bar, so that now we're up here, and we'll call this P1. Is that okay? And these lines may not be very accurately sketched. But in terms of an equation or equations, and this just continues, 1, 2, 3, we can now say that P sub 0 is 700. What's P sub 1? Now we just have to basically rewrite that vertical line at the end of 1 year, or at the beginning of one, or well, above 1 on our time index after 1 year. It's now P sub 0 plus the interest on that balance, P sub 0R, plus U bar, the additional investment. Or this is now 1 plus R P sub 0 plus U bar. And we know these numbers. That's 0.06, and this is 700. And what's U bar? That also is 700, isn't it? Our payment, U bar, the input now to this process is 700 each year. Or P1 is now this 1.06 times P sub 0 plus U bar, or you could write this many different ways, but maybe you say 2.06 times 700. So that P1 is now 1400 plus 0.06 times 700, or 42, 6 times 7, so that we now have a little bit more than twice 700, which if we didn't get any interest, we would just keep adding 700. But now we're getting a little added to that because of the interest of 6%, and that's our $42. And we could just keep doing this. We could now say, okay, P sub 2 is 1.06 times P sub 1 plus U bar, which is 700. P sub 5 is now 1 plus R. P sub 4 plus U bar. Do you see a picture? Another picture besides this graph? Can you now draw a block diagram for what this is doing for us? What's the block diagram look like? How many delay blocks do I need? I just need one, don't I? This is a first order difference equation. Maybe what I should have done is said that this is R bar, since that's not the same R as what we had before, was it? So my R bar is 6%, not the R from before, which was 8%. Now, in this case, we have U bar plus, and here we have 1 plus R bar. There's our picture of what's going on in a block diagram for this account of money that hopefully P sub n plus 1 just continues to grow. Which, if we were following along with our calculator, P sub 5 is now this 1 plus R bar times P sub 4. P sub 4 I did before class, ends up close to 4,000, not quite. So that now the combination of that becomes $4,882.72. So we're almost reaching our $5,000 goal in 5 years, not 10 years that it's taking us to pay off at a higher interest rate. If we went one more step, P sub 6 would be more than what we would need to pay off that $5,000 student loan. And these two sort of examples I know this is a hard pill to swallow, but it might be to your advantage to save ahead and pay it off after you saved it versus buying something and then having to pay it off with interest. Just saying. Not that we obey that at all, but sometimes it has its advantages. Sometimes we can't. Maybe we don't want to save 30 years to buy that home. Then how could we enjoy it for those 30 years? That's why we have this financial system that we have. It allows us to shift money between now and later. Isn't that a candy? But it's also this concept of the time value of money. And now you understand that relative to an electrical engineering class. Let's now look at some of these ideas in a more general setting, let's now look at these concepts of homogeneous and non-homogeneous difference equations. And all this really is saying is we have no external forcing function or no external input. It's probably easier to think about by means of an example. Let's now say that we have x of n plus 3x of n minus 1 plus 2x of n minus 2 is equal to 0, and this is our no external input. We're not forcing that with some external input. We just have x's. Current values of x and previous values of x. And suppose that somebody now says that we can sort of kick this or get this dynamic system going by introducing some initial conditions or initial values onto those variables x. Suppose that x at time minus 1 is 0, and x at time 0 is 1. Now what we want to do is, now we have a dynamic system that obeys that difference equation. How big is that difference equation? Now you've maybe heard of continuous time differential equations having a particular order. How did you determine the order of that system of equations or of that differential equation? Do you remember? What influenced the order of that differential equation? The highest power of the derivative. Now we have a difference equation, and now you're sort of looking at how many delays do we have here? How many delays do we have? 2. This is a second order difference equation, second order linear difference equation. What we want to do is we want to find a closed form expression, x of n equals something, that will provide us with the dynamic behavior of this difference equation. You could recursively generate x at time 1, x at time 2, based on that equation and these initial conditions. You can simply number crunch that out, and that would be a way of solving x at time n. But now on the exam, if I said, what's x at time 50, you go, I don't know, give me some time, give me some time. You could recursively do it, but if you had a closed form expression, you could now evaluate and say, what's x at 50, and generate the number rather quickly. That's what we want to do now. We want to find a closed form solution to this difference equation with these initial conditions. The way that we found solutions to differential equations is a lot of times we just assume a particular structure for the answer. Let's do the same thing here. Let's just assume a solution form. By that I mean let's just let x of n be some unknown coefficient a times a variable z raised to the nth power. Here, this a and z are values that we actually need to find or compute or determine. A and z are values that need to be determined. Just as a reminder, maybe you were finding solutions to your differential equation by assuming a structure a e to the st for a differential equation. I'll just say that parenthetically. Compare with a e to the st for continuous time solutions. Now we're assuming a structure for our difference equation is some constant a times another number z raised to the nth power. We want to find z and a, or z's and a's. If this is now our structure for x of n, we can now write down that same structure if we have x of n minus 1. We just replace little n with n minus 1. And that will go in our difference equation. We can replace it with x of n minus 2. That's just a, the same coefficient, z to the n minus 2. Let's do that. Meaning now we have a z to the n. That was simply x of n plus 3 times x of n minus 1. That's just a z to the n minus 1. Plus 2 x of n minus 2, which is a z to the n minus 2, and all of that was 0 because this was a homogeneous equation. That is just coming from the governing equation that governs the dynamics of this system when we replace x of n with this assumed structure a z to the n. For the different x of n minus 1s and x of n minus 2s, we end up with this relationship. We want a non-trivial answer. That means something that's not equal to 0. A trivial solution, I could say, well, x of n is 0, and that would solve that difference equation. That's trivial. We want the non-trivial or a non-trivial solution. Let's now factor out a z to the n minus 2 from all of those terms. If I factor that out of that first term, what's left? If I had a z to the n minus 2 times something giving me a z to the n, what does that something need to be? Is that okay? Z squared times a z to the n minus 2 will give me that very first term. What if I want the middle term? And the last term? We call these particular expressions certain, or we label these as certain expressions. This polynomial in z inside the square brackets is the characteristic polynomial of that difference equation. If we actually set that characteristic polynomial equal to 0, we end up with our characteristic equation. So that now if this is equal to 0, then all of this is our characteristic equation. If we have a non-trivial solution, then that a z to the n minus 2 is something non-zero, we can divide that out, and we really just have our characteristic equation left. We're assuming we have a non-trivial solution. Now we have this characteristic equation, which says that we have z squared plus 3z plus 2 equals 0. Remember, we're trying to find values of z and a that will solve that difference equation. And this now gives us a quadratic in z that we can solve for z, and at least find the z, or z's. Don't find the z's just yet. Sorry. We'll be doing a lot with z to the minus 1, z to the minus 1, so we will be finding a lot of z's, but don't be having those z bubbles above your head until after we leave. That's what I'm meaning by don't find too many z's. That's kind of lame, huh? All right. Where were we? We're trying to find the z's that satisfy this equation, and this is one of your algebra problems, right? Just factoring a quadratic, and this one is not too hard to find or to factor. We've now solved our characteristic the characteristic equation. With two different values of z. Z equal to minus 1 solves it, and z equal to minus 2 solves it. Now we know that x of n, the solution, is going to be some scalar. So now let's distinguish between our a's. We're going to have two different a's. We have a1 times one of the roots or solutions to the characteristic equation. Let's say the minus 1 to the n. That's the az to the n structure that we assumed, plus a sub 2 minus 2 to the n. Now we go back to what we were maybe familiar with in differential equations. How did we find the unknown coefficients? We could use what we know, which in this case are the initial conditions. We'll find a1 and a sub 2 from the initial conditions. We said x at time 0 was 1. If we now use little n equal to 1, we have a1 minus 1 to the 0 plus a sub 2 minus 2 to the 0. But that just says that we have 1 is equal to a1 plus a sub 2. There's one equation in these two unknown coefficients. We had one more initial condition, and that was x at time minus 1, and we said that was equal to 0. We substitute minus 1 in for little n. What am I doing? I'm z'ing it up here, right? If you're watching more than you're writing, but if you had your head buried, maybe you missed that. That's fine. We now have a1 minus 1 to the little n is minus 1, and we have a sub 2 minus 2 raised to the little n, which is minus 1. This we could now rewrite if we wanted to. We could say this is minus a1 plus, or minus, depending on, that minus is going to remain, and we now have a sub 2 over 2. Or a1 is equal to minus 1/2 a sub 2. So if we can find a1 or a2, we have the other one. Or this is now one equation in the two unknowns. We had the earlier equation right here. Now we can just solve those two equations and the two unknowns. We can now say that we have 1 is equal to a1, which is minus 1/2 a sub 2 plus a sub 2 a sub 2 is equal to 2, a sub 1 is just minus 1/2 of that, or minus 1. And now we have our closed form expression for x at time n. That's a sub 1, which is minus 1, times z, minus 1 to the n, plus 2, that was a sub 2, minus 2 to the n, and that's true for n, let's say, greater than or equal to 0. What's the behavior of x of n? What's it looking like? This is supposed to be some dynamic equation. We start with, before times 0, it was 0 at minus 1. Then at time 0, it's 1. What happens at time 1? Well, we've got the equation. We can solve this for any time we want. Now, it's closed form. X at time 1 is now minus 1 times minus 1 plus 2 times minus 1 or minus 3. We start at 1, we go to minus 3. What happens at x of 2? We have minus 1 plus, or times 1, which is minus 1 squared, plus 2 times 4, or 8, or 7. Uh-oh. Started at 1, went to minus 3, jumped up to 7. What's going to happen next? Can you just expect, or what can you anticipate happening? Will it be positive or negative? Negative. Will it be bigger or smaller than 7? Bigger. In magnitude. Okay, so you got me there. Again, the z problem. The z's. What's going on here? If you had to describe this system, we just started it from an initial condition, and what's happening? It's going unbounded, isn't it? That's an unstable system. That linear difference equation is an unstable system. Could we have anticipated that based on any of our steps in our solution? Those roots in the characteristic equation are related to the stability of our system. What are the magnitudes of those roots? The magnitudes, if we take the absolute value, 1 is 1 and 1 is 2. Where are those points relative to the unit circle? If we looked at this unit circle in the z-plane, this is sort of anticipating future discussion. We now had and I don't have a compass up here, So don't get on to me if my circle doesn't look very nice. But this is now j and minus j, 1 and minus 1. There's the unit circle. These roots of our characteristic equation are actually outside, one of them anyway. One's right on the unit circle. If we just had that root at minus 1, our solution would just bang back and forth. Plus, minus, plus, minus, plus, minus. It wouldn't decay, it wouldn't expand. But since we have that 1 that's outside, 2, it just keeps growing and growing and growing. And it starts dominating the response. Since it's negative, it's helping to introduce this dramatic change in sign at every time step. I'll decide what we do next time. Maybe I'll offline do the non-homogeneous. Maybe we'll do that next time. I don't know. Have a good weekend, and I'll see you next time on Monday. Not in a week.